Biomedical Engineering Research for Healthcare, where we have speakers across different institutions and organizations to share a plethora of knowledge with us for the next 3 days. To start with, we have our first guest speaker, Professor Binzu J. Kailath from Triple ITDM. Ma'am has completed her BTech in Electronics and Communication Engineering from University of Calicut and her MTech in Microelectronics and VLSI Design from IIT Madras. Her doctoral research was based on ultra-thin oxide metal oxide semiconductor devices. Her research interests include neuromorphic circuits, mixed signal IC design, and microelectronics and MEMS. She has various awards in her recognition. Some of them are the National Merit Scholarship, the DAD Fellowship for Postdoctoral Research. She's also been a reviewer for IEEE Transactions on Circuits and Systems, reviewer for Microelectronics Journal by Elsevier, and many others. She is also a professional member of IEEE and a life member of ISTE. We welcome you, ma'am.
Thank you. Thank you for the nice introduction. So, shall we go ahead?
Yes, ma'am. Yes, ma'am.
Let me please share my screen. I hope my screen is visible.
Yes, ma'am. It's visible, ma'am.
Okay. Thank you for this nice, sorry, for nice opportunity to share the some knowledge that acquired in neuromorphics for last 2-3 years, as well as based on the experience in talking with the experts in the field. So this talk is maybe a little long, I'm not sure, but I would like to conclude by 9:45 as I have a class at 10 o'clock. I would try to finish before the time. So I hope we can go ahead with the talk, and if you have any doubts, you can stop me or you can ask at the end, whichever is possible at this point. So the talk is organized like first we will have a brief overview of what is this neuromorphics, why the name has come, what are the recent advances that is happening across the world in this, what are the major industries that are working on this, and then we will go to some specific works by our group. So as you all know, a biological neuron is the elementary processing unit of the brain, and the left side diagram shows the left side diagram shows one neuron, where the right side one shows millions of such neurons. So this is the detailed diagram of a neuron, because I hope the participants would be basically who are interested or who will have some exposure to biomedical engineering or biomedical signal processing. So maybe these things you might be already knowing, but I just want to show that, because this is the basic structure that we try to emulate with an electronic circuit or a silicon circuit. So this is a basic neuron. The neuron has the interconnection between two neurons is actually known as the synapse. So synapse is the one actually controls the talking between neurons based on the inhibitory or excitatory behavior of the neuron. That means it gives out, in terms of electronic circuit, it gives out a current or absorbs a current when we actually emulate in the circuit. And we have the dendrites, which are actually sense or accepts information from other environments, say for example a cold environment, a hot environment, or any type of environment the system is subjected to. and then it has the long axon, and you know that there will be always ionic interactions that happen between the soma, axon, and the outside world, so the out beyond the cell membrane. So based on the charge carriers that move across different membranes, we actually develop a positive or negative potential. Based on that, we create the something known as the axon potential, or the firing. That is how the biological neuron works. So the first generation neural network, or the neurons models, which was based on a thresholding behavior, where the input, the three lines which are given at the input, actually represent the different sensory signals that is coming, all will be summated, and if the net value is greater than certain threshold, you give a constant one, and if the net value is less than certain threshold, you give a low value. So this was the initial model that was given by the neuron. This sigma of Wixi represents the weights and input summation. If it is greater than certain threshold, you get the output 1, otherwise 0. This was the first neuron proposed by McCulloch in 1943. And then came around 1953, the perceptron neuron came up, which actually based on a sigmoidal function. So just the thresholding was not able to emulate the biological plausibility. To improve the biological plausibility, the model came up with the sigmoidal function. So and then came the biological neuron, the third generation, which is the spiking neuron model, where the function is not sigmoid but integration. So it continuously integrates or accumulates the input received, and when the accumulated value is greater than a threshold, it fires as a spike. So this represents a spike. So here, the distance between the spike would actually represent the magnitude of the integrated value. So if the input signal that is sampled or that is encoded is having higher amplitude, the spike generated will be closer. That means the spike frequency or the spike rate will be larger for a larger amplitude signal. So spiking neural networks were given in 1995 by Hopfield. The first model was given by Hopfield. The spiking neural networks are biologically more plausible, computationally more powerful, considerably faster than networks of the second generation. And it is extremely low power when you actually implement in analog and digital circuits. This is one example of, if you actually go through some papers of neuromorphic circuits, these terms you would come across. That is why, the neocortex means bark in Greek, the neocortex model. This is some part of the brain. If you see the neuron models that has come up, these models actually, billions of neurons are there in the brain, so it would be impossible, and each of the neuron actually, or maybe a bunch of neurons behave in a similar way, but not all. So to create a model for each and every neuron is extremely impractical. So what people try to do is they take certain neurons which are dominating in their characteristics and then try to model those. So that is how, this neocortex model, which is at the back, is the occipital area, important for visual processing. So there are many models on this. This is in cerebellum. It contains 50% of all neuron involved in precise timing functions. Then hippocampus, assumed to work as an association area, which processes and associates information from different sources. So the basic analog or digital models that have come up are for neocortex models as well as hippocampus models. Now, these neurons receive input through synapses on its dendrites, and dendrites tree often receive more than 10,000 synapses. So the neuron communicate using spikes, normally of duration of maybe milliseconds excursion, and even sometimes can be hundreds of milliseconds, but not more than that. So few milliseconds to hundreds of milliseconds, that is the normal time of response time for a neuron based on certain sensory input. So 1 millisecond excursions from the neuron's membrane voltage and generated in the axon hillock, from where it propagates along the axon to 10,000 axon terminals. So some release both excitatory and inhibitory neurotransmitters. Some are without action, not all neurons spike. So that is why I said there are millions of types of neuron. It would be impossible to model all. So people actually try to take a specific model and then try to model them. So this is a presynaptic neuron and a postsynaptic neuron. Presynaptic neuron spikes in N1 and N2 represents presynaptic neuron, and NJ represents a postsynaptic neuron. So these multiple neurons like this gives firing at say T1 instant, T1, then another T1, then T2, T2, like that. Multiple time instants, these will be spiked, and this NJ neuron receives all these spike, accumulate all the values, and based on the time difference between this output spike as well as the pre or postsynaptic spike, the relationship between the NJ and a particular N1, N2 can be identified by the distance between the spiking or firing of NJ and N1. That is how the learning process of neurons are actually evolving. So this encoding is known as rate versus spike. I mean spike encoding. The spike encoding can be emulated in circuits using a rate coder. Rate coder is a circuit which actually generates spikes in terms of Poisson relation. Poisson relation means there will be a specific relation between the ratio of the postsynaptic firing rate to presynaptic firing rate. So if we follow that Poisson ratio for the postsynaptic firing rate to presynaptic firing rate, it is possible to implement a rate coder, and that rate coder can be used to model a neuron. I mean, if you give that input to a neuron, it will have the capability to learn or get trained on its own and produce the outputs. So this is one example.
Ma'am, your voice is not audible, ma'am.
I'm really sorry. I was continuously talking here for last.
No, ma'am, it was only for just 2 minutes only. We couldn't hear you. Now it's audible.
Yeah, because I didn't switch off the mic, but mic became off. That is what happened.
Okay, ma'am.
Yeah. Okay, so okay, was it done? This one?
Yes, ma'am.
Yeah. Okay. Okay.
No
No
yes,
problem.
this slide only.
Yeah. Okay. So we can see if you see the equation one, I have taken as a snapshot from the textbook of this neuron models. If you see that, you see this is a complex equation with so many parameters. So this HH model, HH model is like, it is not only this equation, it has multiple other equations with the numerous other around 40 parameters are there. This is the best biologically plausible model. But if you actually try to encode this model or try to emulate this model onto silicon, you will need an extremely high hardware. Then people have come up with other models which are this biologically may not be that plausible, but computationally more efficient. So such models are there, like theta neurons or Izhikevich neuron model or LIF neuron model, like that. So this is the example of Izhikevich neuron model. This So this is the simple equation of Izhikevich neuron model. The membrane potential, the action potential, the capacitance value, the refractory period, all that is involved in this. With that, if you vary these parameters of constants, input current I, A, B, etc., if you vary that, and the threshold also they have given, but we can change it. Actually, if you model for any biophysical signal, it would be required to change this constant. So this is like not universal constant. Based on a specific application, one can tailor this, and then we can use it to encode any analog signal. So these are some the spiking pattern of the neurons are multiple types. Regular spiking is there, intrinsical bursting, chattering, fast spiking, thalamocortical spiking, then resonator. There are two types here where the reference voltage is different and the rate of spiking is also different. Here we can see that the spike frequency adaptation is visible here in this figure and this figure. And here also this is low threshold spiking. So there are actually multiple types of spiking pattern possible based on one model. So one of the most commonly used digital model is Izekevich neuron model. He is a professor from Cornell University. So you can build a network of neurons by interconnecting them, input layer, middle layer, output layer. So here represents X1, X2 are input layer, Y1, Y2 are output layer, and these are intermediate level. It's not like X1 should be connected to Z1, Z2, and Z3. Here you can see that X2 is connected to Z2 and Z1, whereas X1 is connected to Z1, Z3, and Y1. So it depends upon the interconnection between your input variables and output variables. So if you have as many input variables, that many neurons you need at the input. How many output variables you need, that many output neurons you should have. In the intermediate layers, or people call it as hidden layers, hidden layer neurons will be depending upon how many or what are the type of computations that are actually required to model this. So here we can see that there can be different types of back propagation. So during training, there is a propagation of error or a back propagation of error. So with that, you can actually train the neural network. I just gave it as a example. So this learning process can be two types of learning. One is known as supervised learning, another is unsupervised learning. Unsupervised learning represents the neuron has the capability to train on its own. That means, unsupervised learning means neuron do not have the capability of train to its own. We have to make it, we means the user or the designer have to tune the values of the weights such that you get a desired output. This is possible only when you know what is the output that you expect. Say for a classification problem, or from an image classification problem, or a certain anomaly detection problem. If you know that for particular case of anomalies, a certain output should be produced by the network, then you can tune the network or the synaptic weights in such a way that you can actually vary the weights of the synaptics should be varied in such a way that when these type of inputs come characterizing a particular type of anomaly, the output of the neuron will fire. All other cases, the neuron will not fire. So that is type of when the user or the designer tunes the weight on based on some techniques, that is known as unsupervised learning. Supervised learning, where the user has the control of the tuning. Now, how do you tune it? Sometimes, the user, as a first-time designer, we may not know how the network should be trained. So in that case, you can take use of some machine learning algorithms like gradient descent algorithm, or some type of algorithm, linear regression model, or some algorithm we can use. And in the linear regression model, if you plot, you have a bisector line. So you can define your parameters on the x and y axis such that it will actually give you certain weights, and you can start the training using that weights. Whereas if you are a trained designer, you can start tuning on your own. Okay, you need not use any standard algorithm. This is the meaning of supervised learning. Unsupervised learning means the neuron has the capability of learning on its own. It automatically learns on its own, but in that case, neuron should be capable of learning on its own. That means some algorithms should be already incorporated in the synapse of the neuron, and these algorithms are basically known as spike timing dependent plasticity. So if you try to emulate a spiking neural network, which is a combination of the neurons which are spiking based on the input it fires, and if you create a network based on that, then you need to have, and if you want to implement supervised learning for a specific application, you need to implement learning algorithm. And one of the most important or most commonly used learning algorithm is the spike timing dependent plasticity. So the spike timing dependent plasticity simply represents that for a presynaptic neuron and a postsynaptic neuron, as I said before, the time difference between the spikes of pre and the post will actually determine how fast the neuron will fire. So initially, all synaptic connections will have equal weights. The magnitude of the change of the synaptic weight depends on the timing of the spike. So this is the in a simple example. Later we will see the actual equations that represent this spike timing dependent plasticity also. So yeah, so this is the graphical representation of pair-based spike timing plasticity. So A plus and A minus are the constants at 0th interval. The y-axis is actually representing the weight by which the synaptic weight will improve or decrease based on the distance between the spikes. X-axis is it actually represents the timing difference between the firing. So if the presynaptic spike arrives at the postsynaptic neuron before the postsynaptic neuron fires, for example, it causes the firing, the synapse is potentiated, otherwise it is known as depression. If the presynaptic spikes arrive at the postsynaptic neuron after it fired, that is, it brings the news late, that means the synapse is depressed. So based on that, the values of A plus and A minus and the tau plus and tau minus, these are the constants, you can tune it and make the neuron get trained for a specific application. So spiking neural network are composed of neurons and synapses. Neurons are simply any type of neuron model you can use, Izhikevich neuron model, LIF neuron model, or now people started using ADEX neuron model. You can use any of these neurons, but the learning phenomena one has to, which is the most bottleneck process in implementing this, is the biological plausibility of the neuron model, as well as how the learning algorithm should happen. So the learning algorithm, people use spike time independent plasticity. Even in STDP, we have actually pair-based STDP as well as triplet-based STDP. All these are exponential equations, which would require some type of optimizations when you actually implement on electronic circuit. So the neural network consists of cortical spiking neurons with axonal conduction delays and spike timing dependent plasticity. The network is sparse with 0.1 probability of connection between any two neurons. Neurons are connected to each other randomly. Synaptic connections among neurons have fixed conduction delays, which are random integers between 1 millisecond to 20 milliseconds. So the spiking neuron networks are almost same as pulse coupled neural networks. So why we call it as pulse coupled is because the spiking, always this type of neurons compares the spike, which is a pulse spike. When you when you actually see a biological neuron, you get an exponential curve, you get something like this and goes like this. But when you actually see an electronic circuit, it cannot generate only spikes with our pulses. So this spiking neural network we actually encode in the form of pulse networks or pulse generating neural networks. So inspired by neural computation, accurate modeling of synaptic interactions between neurons possible, taking into account the time of spike firing, fast adaptation and exponential capacity to memorize. So these are the questions that people try to answer nowadays. How can we design efficient learning rules that take advantage of this computational model? Can we already show in theory for simple neuron models whether SNN can do more than classical computational models? Do we need very accurate neural model to improve learning? What design principles other than neuron model are crucial for efficient learning? So these are the things different industries are trying to work on. and as well as the scientists from across the globe. As you know, this SNN has come only in 1995, and the industries have started working on maybe last 10 to 12 years. People have started working on this. If you see the earliest paper of neural network, the one of the godfathers, you can say, Mead Conway is the first one who actually proposed this neuromorphic circuits of SNN. But you can say that, in ETH Zurich, Professor Indiveri is there. He is one of the godfathers of neural networks, and his first paper came around 2005. So you could see that this development has come in last maybe 20 years or so. So this is like an emerging area where people can actually, because it emulates the biological behavior, it will have enormous applications if we are able to successfully emulate the neural or biological behavior in an electronic circuit. So as I said, this is Mead Conway, Carver Mead and his students pioneered the development in analog VLSI technology for use in neural circuits. They developed a silicon retina which electronically emulated the first 3 layers of the retina. Okay, so I hope you can understand when you say the retina has rods and cones. It identifies the intensity as well as the color information. If you know all types of photo detectors that are available in universe, maybe up to maybe 1 year or so, we have the photo detectors which can detect only one wavelength. So the wavelength, the photo detector or the photo transistor or photodiode, whichever be the device, it actually works on the principle that the band gap of that semiconductor is should be equivalent to or should be within the range of the wave that is to be detected. So which means the silicon band gap is not in the visible spectrum. So normally silicon will not be used. Some other semiconductors, means 3-5 semiconductors or some other material will be used as photo detectors for working in the visible spectrum. So if we whereas our human eye, we can see that you see the moment you open your eye, you see infinite number of colors. So if you want to emulate the photo detector, you will need infinite photo detectors, each one or each array designated for identifying a particular wavelength. And quite recently, maybe last year or so, there are multi-layer photo detectors have come up which can actually identify maybe 2 or 3 colors. So in the sense, the color actually penetrates. I mean, the light actually penetrates. The first one detects the first wavelength. Some will penetrate through the first layer, then the second layer will be absorbed there, and then the third layer will be absorbed in the last one. Like that, some only in the initial experimental studies. So if you want to actually emulate the behavior of a real retina, that is like a nearly impossible task, in which you want to actually have infinite type of photo detectors. So people come up with array of detectors. Suppose that basically all these are consisting of RGB. So if you can actually develop an array of photo detectors which can do RGB, and these sensory signals, these output of these RGB array sensors, if they are given to a proper integration, then the combination of this RGB can be taken to the cortical neuron of the brain, where you can actually analyze where another circuitry definitely needed for emulating that behavior, so that the visual ability of the person can be improved. Okay, so when we say it's an artificial retina, but huge amount of work is actually required here. Similarly, one can think about artificial ear, but nowadays the hearing aids are very low cost. Hearing aids are possible now. So there also we can actually improve the intelligence based on this spiking neural networks. So the early neuromorphic architectures were artificial neural network chips. Example, in 1989, ETA, an entirely analog chip that was designed for feed forward at ANN. These are not SNN. Then NI100, significantly more powerful, however has narrower functionality. So then Synapse 1 is a modular system arranged as a 2D array of MA16 weight memories, data units, and a control unit. Then came NeuroGrid in 2005. NeuroGrid is a multi-chip system developed by Kwabena Bohan and his group at Stanford University. Its objective was to emulate neurons composed of 4x4 array of neurocores. Each neurocore consists of 256 by 256 array of neuron circuits with up to 6,000 synapse connections. Then FACETS is another project designed by International Collective of Scientists and Engineers funded by the European Union. They recently developed a chip containing 200,000 neuron circuits connected by 50 million synapses. And then TORS, Quiz, etc. 2005 designed an hardware architecture for a bio-inspired neural model for motion estimation. It consists of three basic components to perform spatial, temporal, and excitatory and inhibitory connectionist processing. And it observed approximately 100 times speeding over Pentium 4 and implementation for classification of 128 cross 128 images. Then the industries IBM Blue Brain project, IBM and EPFL, then IBM Almadine Research Center, then Los Alamos National Lab, Air Force Research Lab, New York, then Academia, Portland University, Sweden, then Cornell University, many universities. And these are the industries which are definitely working on hardware implementation of machine learning algorithms, or these are hardcore companies. Then the significant projects in Europe, US and China, Human Brain Project, DARPA, Synapse, SpinNaker, Spikey, True North, all these are SNN chips given by the industries. So now ANN versus SNN, already we said that ANN is simply like computation of multiple weights above a threshold, below a threshold, whereas spiky neural network generate the spikes. So perceptron ANN is well understood because it was evolved in 1950s and people have significantly worked on that. But spiking neural network is an infant technology, relatively infant technology. It has potential for very low energy computation and low energy communication, potential for high information content. So brain-inspired ideas injected into machine learning, recurrent neural networks, few bits per value, and machine learning techniques, backpropagation algorithms being used to train models. So actually what we can do is spiking neural network implemented on ANN. That is how now the research are actually happening on, because the training algorithms of SNN are not that prominent. People try to get the training values using an ANN and use those trained values in SNN. That is how now the circuit has come up. So a single analog device can perform multi-bit operations, but analog has challenges, example noise, precision, etc. So cognitive applications are amenable to analog because of their noise tolerance. So actually people build a combination of analog and digital models. You have analog models of neuron as well as digital models of neuron. Digital model, how you develop is you have differential equation which is in the continuous domain, which will be converted into discrete time domain, and then you use either these domain equations or directly discrete time equations to convert into Verilog or hardware description language, and then you make it into the real. So commercial neural network chips fell out of favor in the early 2000s. Then support vector machine overtook artificial neural networks, and general purpose processors were getting faster, overtaking ASIC. So limited market for machine learning, but now that is not the case. The AI hardware is coming up, and these are some examples of Intel hardware. These are taken from the Intel, these pictures. The version 1, this is a version 1, 15-month effort. Basic design only for inference, 92 TOPs, operations per cycle. This peaks 15 times faster than GPU, and TPU is tensor processing unit. Okay, TPU is that. Version 2 designed for training. A port is a collection of version 2 chips connected with a torus topology. Then version 3, 8 times higher throughput, but because of the extremely high complexity of circuits involved, more heat will be generated because the number of components or number of elements are more. You need. Now we come to, so this is just so far what I wanted to give was a flavor of what is the advancement that is happening across the globe. I have not gone into research given by each team, just the overall view of developments that are happening. Now I would like to give a brief of what is happening in our institute regarding this. As I said before, the spike timing dependent plasticity is a learning rule. Only if you implement that STDP, you will be able to actually train an SNN. So the digital implementation of STDP, reusable spiking neural network architecture, then heart rate classification using TSTDP and VCM, analog neuron implementation, neuron as a biphasic encoder, analog implementation of PSTDP and TSTDP learning rules. These are the things that we have, published works that we have done. I would restrict my talk only on published work so far. So maybe I should this introduction. So the key spiking neural network equations. Now we will see the equations. These are all non-linear exponential equations. Implementing them in digitally is a real task. So the pain point in mimicking these functionalities is that they are highly hardware hungry. So this work aims to propose an idea for using the same spiking neural network for multiple applications, optimize the hardware usage in implementing the SNN by exploiting the reusability aspect of the proposed architecture. The complete hardware design is done using VHDL and implementation on Intel Cyclone 5 FPGA. So this is what we are trying to emulate. Yes. So the pre-synaptic and the post-synaptic equations are this. So this is the spike pre, this is the post spike. So the post spike comes after pre, whereas here the post spike comes before pre. So that represents the potentiation. Here the post spike comes after pre, so that comes the depression. So if you remember, I earlier said that this is reaching late. So whereas this is coming before. Okay, so LTP increase in synaptic strength is done by potentiation. The other one decrease caused by depression. So based on spike timing, interspike interval, that is T pre minus T post, and negative and positive intervals. Based on spike rate, we have multiple implementations on this. So if we implement the actual diagram, which also we have seen, the equations of A plus, this is W, T of W equal to this, e power minus T by tau for LTP, minus T by tau minus for LTD. And if you implement this in digital, this has exponential unit. Many implementations have used multiple methodologies, but all require complex hardware. So a novel method for implementing this is required. So we have come up with a simple algorithm by which the exponential function can be expressed like this. E power x can be 10 power log x, and if you use Taylor series for expansion of e power x, we can approximate the e power x by this function. And now you have to just compute these two values, you can get the exponential functions. So if you see this is from -6 to around +5 variation, but if you see compare the error from -1 to +1, which is the region of interest for -1 to +1 would be somewhere here. If you take those values, the error was only -1.29, whereas if you go beyond the values, the error was larger. So this approximation or this method is usable only when the exponential e power -1 to e power +1 range. So if you want to compute e power 20, this is definitely not possible. But the beauty is that all biological signals have magnitude of the order of millivolts. So definitely this is applicable because our target is to actually identify anomalies in bio signals, say for example ECG or EEG. So then this particular method is suitable for our application because the magnitude is less. So if after implementing this, the actual HTTP curve and the HTTP curve implemented by this was error is very less, and it almost resembled the actual behavior, and the hardware utilization was also less. Compare with the existing works, we find that the hardware utilization as well as the accuracy is better. Okay, so now we come to the second one, the using the spiking neural network for reusable architecture. So this spiking neural network, as I said before, you can see here Isikiewicz neuron model. This is another Isikiewicz neuron model. So one complete neuron consists of these three, which consists of a neuron, a memory, and an STDP. So this STDP weights will be saved in the memory. Those will be used by the neuron for modifying its output. Now, multiple such neurons are connected together, and they are connected to the output layer neurons. So this is an input layer, this is an output layer. Again, the output layer neuron also has synapse, because this way the ratio, the time difference between this neuron spiking and this neuron spiking will be actually used to change its weight automatically and identify certain characteristics. So each neuron consists of three crucial components: memory, neuron, and STDP. And the interconnection between them is a given figure. The address and event representation protocol is the protocol that people use. We also have used the same thing for talking between these elements. You know, when a spike has to be given from one neuron to the another is actually decided using this AER protocol. It ensures proper communication. Input bus has output spikes of all neurons in SNN. It identifies the address of neuron that produced a spike, and it passes on the address to all neurons by AER and sends the addresses of neurons serially if multiple neurons generate spikes in a particular interval. So this is how we trained it using the SNN STDP learning rule. Alters the synaptic weights based on pre and post synaptic rates. Okay, so this is how the application first one, reusability aspect of same neural network, is used for two applications. There will be a RAM1 and RAM2. RAM1 and 2 will be storing the weights for each of the application, and this particular application will be given to a single neuron model, which will be alternating between these two. So to introduce reusability, multiple RAM blocks are incorporated to store the synaptic weights for multiple applications. Application select signal is used. So this will be, number of bits in application select will be logged into the base 2. So you can increase the number of applications. So here we have actually used a gesture controlled robotic arm to control the monitor, control the actuation mechanisms of the arms. Another one is character recognition. So a word D, the letter D, alphabet letter D, that is the example given here. The same SNN is trained for recognizing 6 different binary patterns using this. So this also was done. This is the hardware implementation, and we find that the proposed work actually consists of very less number of neurons, and so the hardware resource requirement was very, very less. Now we come to the third one, the heart rate classification using TSTDP. So yes, so this is the all of you would be knowing because you are from the biomedical engineering background. Normally, we say the beat of the heart represented by the R peak or the R wave, peak of the R wave, location of the R wave, and the distance between successive R peaks will be given as the the heartbeats. And if the person actually suffers from a specific problem, the RR interval or RR time width between the successive Rs differs. So there are multiple classes of anomalies. If the RR interval, the normal value of RR interval actually lies between 600,000 to 100 milliseconds, and you have classifications like tachycardia, bradycardia, multiple forms of variations are there, in which you will have lower RR, wider RR, lower QRS, wider QRS, ectopic beats, etc. So all these anomalies, because this neuron encoding is a process by which you try to encode you can use the ECG to encode it, and then you can identify. So, but in this application, we have used a Python method, Python-based formulation for identifying the RPEAK, because that time the system for the identification of R from ECG was not developed, but now we have actually come to a level that from an ECG we can actually identify the RPEAK by the system itself. This paper, that time we were using a Python model for identifying the RPEAK. So the ECG waveforms will be taken from MIT database, and from those database, using the Python model, we can identify the RR. These spikes actually represents the location of the R. Now, if this R is given to a BCM classifier, we can actually classify whether the heartbeat is great. So here the assumption is that when the heartbeat is 60 to 100, it is taken as a normal heartbeat, and above greater than 100 and less than 60 are considered as low, I mean either high or low heartbeat. These we have. This we have a model using a BCM, we'll come to that, Bynum-Stock-Cooper-Munro model. So this was the purpose. We can actually, okay, let me just. So here what we see is that, as I've said before, we have pair-based STDP as well as triplet-based STDP. There are two equations, the weight of the PSTDP, this is the correct equation, A plus e power minus delta by t tau plus, A minus e power minus plus delta by tau minus. Whereas if you do the triplet based STDP, here you see always the time difference between the pre and the post. This is the pre and this is the post. So the time difference between the post and the pre is always compared, whereas here it is either one pre and two post or two pre and one post. So always the time difference between these two. So delta T1 and delta T2 are defined like delta T1, delta T2, T3 and T1. So this is how we actually define the time base and these equations. Now this TSTDP has a property that if you properly manipulate the values of A2 and A3, we can actually get a BCM behavior. So this is the typical BCM characteristics. The beauty of the BCM characteristics is such that it can be used as a classifier, by which if you define the threshold of the BCM, we can actually say something is less than the threshold or greater than the threshold. So this is the fundamental equation in a PSTDP TSTDP equation. The weight is the equation actually represents the weight, whereas in BCM rate of change of weight is given as the equation. So if you make in a TSTDP A3 minus and A2 plus to be 0, you get the modified equation like this. And in this, if you adjust the threshold, the spiking rate of the postsynaptic and the presynaptic by the Poisson ratio, we can actually emulate the BCM characteristics. So this was implemented using floating point algorithm, and we obtained BCM characteristics with the second order curve fitting. We got this BCM characteristics, and using that BCM characteristics, we tried to characterize the input ECG as normal or abnormal. And here we can see that the blue line is the middle line, which represents 60 to 100, and anything less than and greater than will be identified as a low or a high. And so, I mean, these are the characteristics obtained for different cases of heart rate for different ways of lambda, that's given by the ratio of rho, the pre and the postsynaptic spike rate. And here we get the different threshold value. Based on this, we can actually identify whether something is low or high. Yes. So this is the characteristics. We have taken multiple ECG values, and the actual heart rate was coming to be 89, 92, 96, etc. And this was identified as low, normal, high, etc. This is the complete, and the work was compared with multiple papers, and this was published. To analog neuron implementation. So these are the basic, as I said before, there are digital models as well as analog models for neurons. This is a simple analog model where we can actually use for force stacking technique for reducing the power. This is an IAF, integrate and fire neuron analog model implementation for low power. So this is the IAF neuron model implemented for low power architecture with the force stacking technique. Force stacking technique is here as well as here in these two. Remaining everything is the same. In these two places, force stacking technique is implemented. So the property of the spiking was analyzed using different types of spiking phenomena. And now we come to neuron as a biphasic encoder. This was a very good work where the conventional neuron encoder architecture, because the neuron identifies positive, or when the signal is positive, if your threshold voltage is some positive, say 20 millivolt, it can identify only voltages greater than 20 millivolt. Whereas if you want to use it as an analog encoder, analog signal will have both positive and negative. For example, if you take the ECG itself, you see that the PRT waveforms are naturally positive and the Q and S are negative. I mean, if considering no anomaly is present. So in that case, you can actually encode the positive waves PRT, but it would not be possible to encode the negative waves. So there should be some mechanism. Then people came up with the idea of using biphasic encoder. So there will be some phase shift introduced for the signal, such that the negative signal, such that both the positive and negative can be encoded by the neuron. So we have actually given a modified version of this. Okay, this is like cortic neuron. Another analog neuron model is cortic neuron model. We have, this is only, there is not much contribution from our side. We try to use it for low power application. That is the only thing, but different spike pattern are not possible to be generated. That we have done. That is the only thing. Yeah. So the adaptive exponential neuron firing, that is what a major contribution from our part. This we have used for as biphasic encoder. So this adaptive exponential neuron, which we developed using a low power implementation, was using very low power for the input current range from 10 micro to minus 10 micro to 10 micro, as well as minus 100 nano to 100 nano. Similarly, the delay was a little higher. That anyway, definitely whenever the power reduces speed, the delay will, power and the delay are actually complementary in nature. But now we have got a better result. This is the published result maybe 2 years before. So 39.4% lesser energy per spike, and at least 100 picojoules less energy for spike frequency adaptation. So this is the summary of the work. Now the major contribution is on this, the biphasic encoder. People use 2 neurons for identifying that, whereas we have come up with a single neuron with only one DPI, differential pair integrated circuit, was only used for the input source and 180-degree phase shifted input. This only 2 circuit which were required is this input DPI and input DPI for encoding positive and negative. Then it will be the same neuron architecture which will be given, and that one we encoded a simple sinusoidal signal. This is the spike generated for positive wave, and this is the spike generated for negative wave, and this represents the reproduced signal and original sine wave, and this represents the error. And error was coming only, signal to error ratio was coming only 60.84 dB. It's extremely good result, and this was giving effective number of bits of 9 bits encoding process, ENOB, and the power was only 115. But it was only a simulation, not an experimental data. Definitely simulation will have, but experimental maybe it may go to maybe a few microwatts. Now, effect of spike frequency on signal to error ratio and power comparison for different frequency of input signal. We have compared the signal to error ratio and power, and we found that how we calculate a signal to error ratio is ratio of the power of input signal to the power of the error signal. Effective number of signal is identified by referring this paper. SNR minus 1.6 is an empirical model by 6.02, and figure of merit is given by power divided by 2 power NOB times twice bandwidth. So that is how we found, and we found that the result is much better than existing result. Okay, so the proposed ADAX neuron, you can see energy per spike, static power dissipation, spike frequency adaptation, everywhere some improvement is there. Now I come to the last model where we come up with, so this is the low power INF spike frequency adaptation. If you simulate on, this is from LT-SPICE result, where we have simulated different types of synapses also. This is current mode integrator synapse, and the different transistors, how they operate, and we simulate the circuits based on this. And if we want to create an analog model for HTDP, there were some circuits. So this is the equation that we have to model. So this A plus e power minus t and a minus. So this PSTDP circuit, this is the circuit which was already there, where the current through this transistor, actually the potentiation behavior as well as depression behavior should be modeled by a circuit. So potentiation behavior means actually the weight or the magnitude of voltage at that drain of the transistor should be increasing. During the depression, the reverse should happen. So the voltage difference in this in one transistor, the VG and VS minus will be adjusted in such a way that the current pumped from that onto another transistor will be adjusted. So more current is pumped onto means the voltage will be increasing. Less current is pumped onto means voltage will be decreasing. So that is the principle used for this PSTDP. This is the existing model. And the TSTDP equation, because the TSTDP can only emulate the classification behavior. So this is the circuit that we have proposed, using transmission gate phenomena. We have combined, or not exactly combined, we have used the existing PSTDP circuit with some modification for implementing this triplet based STDP circuit. And we got the similar characteristics as that of for potentiation as well as depression. And this was possible to give the BCM behavior also. The proposed TSTDP circuit exhibit BCM learning behavior. Poisson spike train lambda, that is the spike rate of pre-spike to spike rate of post-spike was 1. That was exactly followed. And VW is the compared with the experimental data provided in 3. And we find that we have got a really good characteristics. And this was used for classification problem given in paper 2, and we have done that. So now, once the leakage issue of CW is fixed, TSTDP circuit can be used integrated with low power INF neuron and CMI synapse to form analog SNN. Even a single neuron with TSTDP CMI synapse can also be used for applications like simple pattern classification. Power of TSTDP circuit in making SNN is to be used for much more complex applications. So these are my so now we come to another neuron model where this behavior can be modeled using a memristor. So as you know, memristor have quite recently, the interest in memristor have significantly come up, where memristor, because of its hysteresis property, that means it is capable of retaining certain information regarding the voltage and the current which was applied to it a certain time before. That is the behavior of the memristor. So the current value of the memristor will have some information on the previous value applied on it. That is the meaning of possible capability of retention of memory. So that property of the memristor is utilized for implementing the TSTDP. So the HP Labs first published the memristor device, a silver silicon based memristor, and we used that memristor model for these were the equations given for the model, and we used that for implementing the TSTDP equation. So we have the circuit for combining proposed TSDP with the bistability. We have the circuit for implementing bistability, then modeling suitable memristor in SPICE, then framing the idea of time division multiplexing based memristive synapse, circuit for implementing TDM based PSTDP, and combination of that. So that is how we achieved this implemented in TSMC 180 in LT SPICE. So this is the bistability circuit. And these are the results obtained. We can see that the weight actually reduces here for the spikes generated. So two terminals T and B represent the top and bottom electrodes of the thermistor. Okay, so this is the memristor characteristics. We can see that the voltage and the current relationship, x-axis time. This is the voltage. Second bottom one is the current. We can see that the value of the voltage and the current, you see here is high, here it is low in the right side. So that we can actually see this behavior we have used here. We have a pre-neuron and pre-output circuitry, a memristor, and then we have post circuitry. We were able to successfully implement this for the first time. Both LTP, yes, this is the circuit. So this is the pre-output circuitry that we have used. A memristor was used to interconnect them, and a post circuitry. This implementation we have done, we were able to accurately develop the LTP LTD behavior of PSTDP as well as TSTDP equations on this. For triplet based STDP, LTP2 and LTD2, two more were added to implement the TSTDP, and we have got the exact behavior as that of the TSTDP. So the proposed memristor based TSTDP circuit has solved the issue of charge leakage without compromising the storage of multiple levels of synaptic weights, and experimental results prove that AG silicon based memristor is compatible with the CMOS. So this can be a potential circuit for future application. It can be implemented, used for analyzing the ECG, EEG behavior. So these are the references. And actually, I would like to acknowledge my students who have completed studies. Sati Jodi, he was a BTech student. He is working with NVIDIA now. He has published 3 papers during his BTech. Pavan Sai, he also has published 3 papers during his BTech. He is now in MathWorks. Madhuvanti Srivatsa, she was a dual degree student doing BTech and MTech in VLSI. She also published 3 papers, and she is now doing PhD at ISC Bangalore. Amrita Manoharan, she graduated in 2020. Other 3 students graduated in 2021. And Amrita works in NXP Semiconductors. The student who worked in 22, their work are, we are in the review process. Reviews and revisions are going on. So I have not, because the results are not out, I have not put their names. So these are the papers that we have so far, around 17 papers we have so far in this area. Thank you for your patient listening and valuable time. If you have any queries, please.
Thank you, Dr. Vinsu Kailath, Professor, Department of ECE, IIII TDM, Kanchipuram, for your wonderful presentation on this neuromorphic circuit design, madam. You have just shown how to create electronic circuits that mimics the functionality of the biological neuron network. You also have shown how to particularly create a spiking neural network model that was very useful. You also shown us how to implement both analog as well as digital way the neuromorphic circuit design, particularly the complex and parallel implementations that you have shown. Your idea of approximating the exponential function was very useful to probably the participants. And as a part of the second part, you have shown us how the spiking neural network can be used for biomedical applications. That was well taken probably by the participants, madam. As you said, this neuromorphic circuit design is an area of active research. On behalf of the Department of Biomedical Engineering, SSN College of Engineering, as well as the FDP coordinators. It is my pleasure to thank you for your excellent presentation on the topic of neuromorphics design. I leave the forum for questions from participants. If there is any, you can unmute and ask. And if there's anything, if you wanted to, you can also put it through chat box.
Thank you, sir.
Is there any questions for participants? You can raise your hand and or.
Good morning, sir, and good morning, ma'am.
Yeah.
Am I audible?
Yes, yes.
Yes. Yes, sir. This is Mrs. S. Alagu from Madras Institute of Technology. Good morning, ma'am. Excellent works compiled by you. It was a wonderful presentation. Well, thank you so much. I have two doubts. First one is, in what are the different applications where we prefer BCM classifier? And second thing is how the reinforcement learning differs from unsupervised learning. There is always some cloudy things available in between that. So I want to clarify that. Thank you, ma'am.
Yeah.
These two questions. Yeah.
Yes, ma'am. Thank you for your nice words. I am not sure whether I would be able to clearly give on reinforced learning. Anyway, let us come to the first question, the BCM classifier. Ma'am, BCM model is traditionally used, it was given by Gressner, and it is used for whenever you know that certain thing to be classified based on a certain threshold. Okay, then the BCM classifier can be used. So if you have no, I mean, if the classification is not based on a threshold, then BCM classifier cannot be used. So if you know the limit of, say for example, let us come to this, tachycardia, bradycardia type of anomalies of arrhythmia from ECG. So if you say that above 1200 milliseconds of ECG, so is my ECG RR, because RR, you take a ECG measurement of 3 minutes, you actually get say maybe 50 or 60 cycles of ECG. So this 50, 60 cycles of ECG with the spikes coming up, these come at the rate, in this millisecond, you need to actually identify whether the RR interval is larger or smaller, etc. So if you have some, in addition to identifying what is the value of the RR interval, if you know that it is above 1200, above 1200 you classify it something, below 1200 you classify it something, then BCM classifier is used. So in other words, I would say that if you know the threshold limit of certain normal range and abnormal range, then BCM classifier is preferable.
Thank you so much, ma'am.
And it's a very, very highly biologically plausible model.
Okay. Thank you, ma'am.
And second question is about reinforced learning and supervised learning, right? Yes, ma'am.
And unsupervised learning and reinforcement learning.
Yeah, and yes. Actually, I am also not a very good expert in this. I just started in last 3 years. So we have now come to the level of, training the SNN with the supervised learning, where we know that this is the output that we want to get, and we try to tune the model and produce the output for certain type of classification. And we are working on STDP and BCM, which is supervised learning. So reinforced learning on SNN, I have not worked on so far, ma'am. So I'm very sorry, I would not be able to give more details on reinforced learning now. Maybe if I am given an opportunity, maybe after a year, I would be able to give you maybe more detail. Sorry, ma'am.
Thank you so much, ma'am. Thank you, ma'am. No problem. Thank you, sir. Thank you for that.
Yeah. Thank you, Dr. Binsu, madam. I understand that you have again one more lecture in your department right now. Thank you for in between. You have accepted our invitation for presenting this lecture. Thank you so much, madam. Thank you.
I can log out, right?
Yes, madam. You can log out.
Yes, ma'am.
Thank you.
Ma'am.
Thank you, everyone. Thank you.
Thank you.